Professor Asegun is back. He's an alumni from Gongchen's group here, and he graduated in 2009, I guess,
Correct.
from here.
Yes.
And since then, he's done a lot of things. Actually, he worked at Oak Ridge National Lab as a postdoc with David for some time in the back, and then he was also working at Northwestern, and then joined ARPA-E as an ARPA-E fellow. So he's seen a lot of different aspects of research and development and exciting opportunities, and then he joined Georgia Tech's faculty in the Department of Mechanical Engineering. We're really excited to have Ase back here, and today he's going to share with us his work on thinking beyond the phonon gas model.
Yes. Thank you for the kind introduction. It's great to be back. I'm very excited to come and talk about some of the stuff we've done since I left. This is generally about half of what I work on, so I do two main things. Still doing molecular dynamics related work, which is what I'm going to talk about today. Maybe next year I'll come back and talk about the other half of what I work on, which is actually prototype development for high temperature solar thermal applications. So there we're doing some things with transporting liquid metal. But here I want to specifically focus on our work at the atomistic level and trying to understand phonon transport and think about it in a different way. Really, let me quickly give an outline of the talk. I want to talk about really quickly what are phonons, just for those who may not be familiar, but also for those who are familiar, just to kind of give my perspective on what it actually is. What is a phonon, and what is this notion of the phonon gas model? And then I want to talk briefly about how I believe we came to use and leverage the phonon gas model as our primary lens for understanding phonon transport, and how it became really the sole lens that we use for understanding phonon transport. And then I want to talk a little bit more generally about some situations that we've identified where the phonon gas model becomes somewhat problematic because there's a bit of an inconsistency between how the modes are defined in other systems and the issues that you have with trying to define a phonon velocity very specifically. And I'll talk about amorphous materials. I'll show some results for amorphous materials, alloys, spend a lot more time on talking about interfaces between different materials, and then I'll talk a little bit at the end, if I have time, about individual molecules. So real quick, what is a phonon? Well, our general picture of what a phonon is essentially comes from this notion of a homogeneous crystalline material that's essentially infinite and periodic in all dimensions. And the idea is that in such a system, the atoms vibrate around equilibrium sites, and those vibrations can be broken up into a series of sine or cosine waves or plane waves that propagate. And the idea is that these waves have a certain wavelength associated with them, and each phonon or each mode of vibration has a certain frequency associated with it. Now, the frequency gives you the energy, and that's the only part that actually is critical for it to be a phonon, is that you have an oscillator with a certain frequency. But in the context of a crystal, we generally associate them as having a wavelength. We can define a k vector. Then we can talk about a speed, a phase velocity, and also a group velocity, d omega dk. And ultimately, the idea of a phonon is that with these waves, they have quantized amplitudes. So these modes, or these amplitudes, are quantized and have discrete values, and each jump in discrete value of amplitude corresponds to a certain amount of energy, and that energy now is associated with a quasi-particle, or effectively we treat it as a particle that has the same velocity as the wave, and it carries energy just like the wave would, but now you can think of it in terms of a gas of particles, and these particles can interact. That's the main difference between it and a photon, so to speak, and these phonons can interact with each other. They can interact with defects or other kinds of imperfections inside of a crystal. They can also interact with boundaries, as shown in this picture to the other side here. So they can scatter from the boundaries. And ultimately, we can use a similar formalism, just like kinetic theory, where you talk about a gas of particles to describe the thermal conductivity, where it's basically a third heat capacity times the velocity times a mean free path. And here, the idea is that each of the phonons may have different properties. They may have a different specific heat velocity and mean free path, and so you just have to integrate or sum over all possible phonons in the system to get the total. Now, how this became our primary lens is that the basic idea is that it works. It basically explains most of the phenomena that we see. So one of the easy things we can explain here is like classical size effects, where if you think about a nanowire, if you decrease the size or diameter of the wire, the thermal conductivity goes down, and that's because the mean free path goes down, because now the distance between collisions of the phonons gets smaller, and so we see thermal conductivity go down. And we've made quite a bit of progress recently, also looking at developing methods to actually calculate these intrinsic mean free paths associated with phonon-phonon interactions. This is some of my master's work where, for example, we built a model that allowed us to see that, for example, in silicon at room temperature, phonons with mean free paths longer than about a micron, there's very few of them, but you can see on this plot that they contribute very substantially to the thermal conductivity. And so we've built some models that allow us to actually extract information about phonons directly from molecular dynamics simulations. There's been quite a bit more work done by David Broido, Keyvan Esfarjani, and others looking at doing some of the similar types of calculations directly from first principles, where we no longer have to make assumptions about the potential or the interactions between the atoms. And ultimately, you see excellent agreement between the theory and the experiments, falls almost right on top of the data. And we can, again, explain effects like size effects in structures like this, where you have micron size features. And even there's been some great progress in the recent years looking at actually experimentally measuring several points along the accumulation curve itself to actually identify what fraction of the phonons contribute to the thermal conductivity that have mean free paths below a certain amount or above a certain amount. And so the fact that this phonon gas model works in all these cases is really what's given us so much confidence that it's the right way to think about the system, the right way to think about the transport. Then we've also extended this idea to think about other materials. So because that's our primary lens, we use it also in the context of an alloy. So you can think about an alloy. Well, what do? Well, we say the heat capacity and the velocities are essentially just like they would be in a crystal, but now you have a virtual crystal, which has modified properties that are somewhere between the two endpoints. And the key thing is that now the alloying elements serve as like scattering centers. And so the main thing that changes is the mean free paths get smaller. But it's still the same idea that you have these propagating modes and their mean free paths have now shrunk down. And this, again, has great consistency, at least qualitatively explaining the behavior in different materials. Then if you think about interfaces, we've used, again, the phonon gas model. We've got a variety of different models like the acoustic mismatch model, diffuse mismatch model, wave packet methods, as well as the atomistic Green's function method. And ultimately, from some of these methods, you see some general qualitative agreement with experiments that is on the right order of magnitude. And so we generally see that these things kind of make some sense. And so there's been some general satisfaction with the degree of explanation that you get from a phonon gas model type picture. All right, so I'll move on from this. But then you can think about trying to now take that physical picture and now make an extrapolation. Okay, so suppose I have phonons that travel a certain distance. So it'd be really difficult to rationalize how it is that a phonon would be able to travel less than maybe one interatomic spacing. And so David Cahill came up with this idea of a minimum thermal conductivity, which essentially said that there's some minimum mean free path that you can imagine for a phonon. And in the 90s, measured a number of different samples, and essentially everything sits above this minimum thermal conductivity limit. But then later on, in around 2007, found some materials that somehow got below this limit. And so it becomes a little bit challenging to rationalize how do you get far below, not just a little bit below, but far below this limit, where you're still looking at it in terms of some now extremely, extremely small phonon mean free paths. So what else is there? Well, what we're essentially proposing, or what we've started to look at, is considering another dimension to the problem. So instead of always saying the difference between a crystal and any other material is just the mean free paths are the only thing that we're always tuning and changing, and the only thing you always have to play with is mean free path, why not actually rethink the modes themselves? And so there was some work done by Allen and Feldman back in the 90s that looked at amorphous silicon. And what they identified by doing a lattice dynamics calculation in amorphous silicon is that the modes themselves actually change. So not all of the modes themselves are propagating. Not all of the modes have a well-defined wavelength and a velocity. And so therefore, they don't really fit into this picture of the phonon gas model very well. So what they noticed is that in reality, in something like amorphous silicon, you have these modes called propagons, which look very much like the propagating modes we're used to thinking of in terms of a phonon. But then the majority of the modes were these kinds of modes, like diffusons they called, which had the polarization vectors or the displacements for the atoms seemed to point in all kinds of random directions. But these are, in fact, eigenmodes. And then you had localized modes that are localized to even just a couple of 5 or 10 atoms that are vibrating all together. And so this, I think, is an interesting taxonomy to take a look at, because this is a good foundation, and we've seen in a couple other classes of materials that these same types of modes, these same classifications of modes show up in alloys and at interfaces and different kinds of situations. And we're interested in rethinking and maybe thinking beyond just the phonon gas model and actually think about treating the modes themselves differently. They actually consider different types of modes and how they may transport heat could be distinctly different than a propagating mode. So let me talk a little bit about what exactly do I mean by a mode. So what you're seeing here, and I'll replay this video in a minute, if we take two crystalline materials, lattice matched, and all I've done, there's no change in stiffness on the two sides, but this side has one mass and this side has a mass that's 4 times larger. You will actually, if you do a lattice dynamics calculation, which basically amounts to solving the equations of motion in the limit that the interactions or the forces between the atoms are all linear or harmonic interactions, then you'll get a series of modes, and some of those modes don't look like the typical sinusoidally varying modes that we're used to, even though the entire system is crystalline. You'll get some localized modes. This is an example of one that's actually localized right at the interface. So the only atoms that move in this quote-unquote mode, in this one solution to the equations of motion, is a mode that actually is peaked right at the interface. And you can see that some of the atoms are moving in one direction, some of the atoms are moving in the opposite direction. So what makes it, so to speak, an eigenmode, a characteristic mode, is that when the atoms move in exactly those directions with those exact proportions, that mode is self-sustaining. If we don't excite anything else, this, what you're actually looking at, is a molecular dynamics simulation. This is at the beginning of the simulation. And 1 nanosecond later, you see the exact same vibrations. All right, so I'll restart that again. You can see a nanosecond later, you don't see coupling to other modes. You don't see anything else being excited. So these modes are self-sustaining, even though they are localized. Just to show you the contrast, if we take this same mode, we slightly change a few of the polarization vectors, swap their directions, you'll see that it immediately will couple, and you'll see all kinds of other vibrations get excited from the outset. So these eigenmodes are special vibrations. These are collective vibrations where all of the atoms will swing past their equilibrium position in the exact proportions to maintain exactly one single frequency. And these are individual solutions to the harmonic equations of motion. And so what we use is we use these as the basis with which to interpret the simulations that we do in molecular dynamics, whereby all the interactions are anharmonic. So we include the anharmonicity, but we project them onto the harmonic solutions so we can interpret them and try to understand which modes are contributing what to the thermal conductivity. So over the last 2 years, we've developed 2 new formalisms, the green Kubo modal analysis method and interface conductance modal analysis method. We have papers that are in review right now in Nature Communications and scientific reports on these 2 methods. And the idea here is that what we started out with is if you could take this modal analysis method and somehow integrate it into an approach like the green Kubo method, which now doesn't require you to define a phonon velocity, but somehow integrate the modal information directly, then you could directly calculate the contribution to thermal conductivity or even interface conductance without having to think about the velocity or having to define it in the context of the phonon gas model. And so it took us 2 years to get the math right, but at the end of the day, what it basically amounts to is that we're going to compare, on the next slide, to the Allen-Feldman model, which is essentially looking at modes in a amorphous material, but only considering the harmonic portions of the interactions. Then looking at doing MD with our new method using the green Kubo modal analysis method. And what we're doing is we're projecting the molecular dynamics trajectory onto these modes that you get from the harmonic solution. So what an MD simulation is assume you have some model for the interactions between the atoms. That model can be very complicated, can have lots of nonlinear terms. Then you just simply evolve Newtonian equations of motion, F equals ma, and you can track the positions and the velocities of the atoms in time. So once you now have the time history of the positions and the velocities, you can then project that onto the normal modes. So what does that mean? Well, so imagine I have a mode. For that mode, I have a direction associated with a given atom that the vibration should occur in. I could take the actual displacement of a given atom at an instant, and I can take the dot product between its displacement vector and that polarization vector. And the extent to which they align and have the appropriate magnitudes will tell me how much of that atom's vibration is due to that mode at that instant. And what that allows us to do is then track the mode amplitudes in time. And that essentially gives us all the information we want about the anharmonic interactions between modes. Now, what we did, this was our special contribution here, because that approach had been done before, was to now integrate this into actually calculating the modal contributions to the heat flux itself. And so how we did that is we actually calculate the modal contributions to velocity, substitute that into a operator for the heat flux, which depends on the velocities. And what you get now is a heat flux that is equal to a summation over modal contributions. So at every instant, we've now broken up the heat flux in an equilibrium molecular dynamics simulation. We're not imposing a heat flux. And you can break it up into a summation over all individual modes, and it sums up exactly back to the total. Now you take that total heat flux, replace it with the sum, and replace that sum in an expression like the green Kubo thermal conductivity expression, where you have a correlation function between the heat flow and itself later at some time. Now you have individual mode contributions to these correlation functions, and now you can see what each mode's contribution is to the thermal conductivity individually, and this doesn't require that you define a phonon velocity. So all you have to do is do any system where the atoms have a stable equilibrium position. They oscillate about that position. That means you can do lattice dynamics of the entire structure. You can get the modes. Then you take those modes. You don't have to make any assumption about whether they're longitudinal, transverse, optical. None of that matters. You plug them directly into the green Kubo expression and get the thermal conductivity contribution for that mode directly. What you'll also see, what we can also do though, is we can take this summation and plug it into both of these terms. And now we can have an entire 2D matrix of all the cross correlations between every mode. And that's actually going to tell us about how much one mode is interacting with another mode based on the extent to which they're correlated in time. And so this allows us to get new access to understanding how these different vibrational modes interact with each other, and it's going to give us a lot more detail. So I'm going to show you some examples of this in a minute. So first thing we did is we take this new approach, this green Kubo modal analysis approach. We applied it to crystalline silicon, and we verified that we get a similar accumulation curve that you would get from a classical approach where you use relaxation time. So this at least was the first bit of confirmation that modal heat flux actually does mean that, and that modal contribution to thermal conductivity actually does mean that. We also see if we group the modes by transverse, longitudinal, and optical, we get the same contributions attributed by the GKMA method as with previous methods. So this, again, gave us some confidence that the method we're using actually does have that same physical meaning, that thermal conductivity contribution you're calculating actually corresponds to that mode. Then we went and looked at amorphous silicon. So now what I'm showing is this is the thermal conductivity accumulation function. So in gray is the Allen-Feldman approach, which basically only included the harmonic portion of the interactions. Essentially what it says is that the only way two modes would be able to interact is if they overlap and they have the same frequency. So they have to have a matching frequency. Our approach is anharmonic, so it allows any mode, even if their frequencies are not the same, to interact. And they postulated, because their method actually has decent agreement with the experimental data, that it's confirmation that you don't have any interactions between different modes with different frequencies, so you can treat it harmonically. However, even though our accumulation looks similar, so suggests that their result is consistent with ours, when we now go and calculate this 2D mapping of the correlations, we see some of what they saw in that this diagonal here, this is a symmetric plot. So the diagonal represents the correlation of one mode with itself. These are like the autocorrelations. That means it has the same frequency. So that's the portion that they would have calculated. But you see significant peaks outside there. So you see that there's significant correlation between modes with different frequencies, which suggests that even though we get consistency in terms of the the accumulation itself, that there are in fact interactions occurring between modes with different frequency. Now, we've also done similar calculations. We're working on calculations for alloys. One of the first things we've noticed is that you get propagons, diffusons, and locons in alloys. So this is a silicon germanium alloy, and you see these same types of mode classifications. And so again, just like in the amorphous materials, you see that most of the modes look like this. They're actually diffusons. And so this brings into question whether the virtual crystal approximation that is often used is even valid in terms of the physical picture that it presents. All right? So granted, you may get good agreement with the experimental data, but there could be some questionability in terms of the accuracy of the physical picture and it being consistent with what's actually happening at the atomic level. So we're in the process of now running calculations to actually determine how much each of these classification of modes will contribute to the thermal conductivity, and that should also be out soon as well. But this is just, an initial calculation to show that these same mode classifications show up even in a crystalline system.
How do you decide? Of course, there's a continuum of modes, right?
Yeah.
And so, like you mentioned, you've got taxonomy here.
Sure.
There's some. What criteria did you use to decide this one is a locon and this is a diffusion?
Excellent question. So locons are easy to find versus the other two because these are localized. So the inverse of the participation ratio will show a peak, so you'll see it rise when you get to localized modes. These are harder to find, but what's interesting is I've actually seen one of my students will pull it up, and so we can scroll through mode by mode, right? And so you'll see modes that look like this, and then it'll seem like he'll go through about 100 different modes, and then it'll finally start to look like this. What's interesting, though, is that 100 modes that he traversed and went through before it went from this kind of character to this kind of character is actually over a very narrow frequency range. So there is a well-defined range of frequencies where you do see this switch in character. Now, right now we've been doing it visually, but we're developing some more straightforward quantitative techniques using structure factors to actually determine the difference between a diffuson and a propagon. So we've gone up to tens of thousands of atoms and still seeing the same kinds of behaviors.
Because it's not influenced by boundary motion, right?
Exactly.
You say this kind of motion and this.
Yes.
Of course, it's easy to look at that and focus on a few sort of features that the eye gravitates toward, right?
Correct, yeah. So we do these in, these calculations, for example, are performed with periodic boundaries. So then as you scale up the size of the system, what you'll find is you'll start to get more and more propagons. So these are generally the low frequency modes, and as the system size gets larger and larger, their population gets filled out. But you get these even with a really small system. Any other questions on this? Yeah.
What would change if you didn't use periodic boundaries?
We could do it. I think what you'll find is you'll probably get even less of these. You'll have to go to a much larger system to see these propagon modes. And then you'll see some modes that are probably all around the surface of this now nano box particle, so to speak. But in essence, I think you'll still see the same types of modes. Yeah.
Would you still be able to use that same decomposition?
Yes. So that's the beauty of it, is that the decomposition has nothing to do with whether you use the periodic boundaries or not. It's general, and you can use it. Anytime you can do the lattice dynamics calculation, you can plug the results of that into Green Kubo now. Yes?
So what is, again, the criteria that you are using to distinguish the diffusion? And another question. If you have a collective mode, it seems to me that collective mode already implies that you have some kind of propagation, because a collective mode means that a unit cell which is here knows what the unit cell over there is doing. That is some kind of signal. If you excite this one, the signal will propagate to this one in order to create this, collective mode.
So let me address the first question. So we thus far don't actually make any distinction between propagons, diffusons, or locons. We treat every mode the same. What you'll see as I go forward, you'll see that actually some of the results, you'll see the correlations actually are distinctly different. You'll see distinctly different features where you see the mode character change, but we don't have to impose any of that. To your second question, we are in the process of trying to build some robust modeling techniques to actually try and understand how does a mode that looks like this actually move any heat. it's weird because it doesn't really propagate. I know what you're saying, that it's a collective vibration, so clearly some information must be communicated through the structure, but it's difficult to tell. So I don't have a great answer for it right now in terms of how does that happen, but these are just simply the solutions you get to the equations of motion, the harmonic limit. It's difficult to say how does a mode like that move heat. All right, so let me talk about interfaces. So in the limit that you have, let's say 2 crystalline materials, A and B, you form, let's say, even a lattice-matched interface. In general, I'm going to refer to material B as the one that's, let's say, heavier, meaning that it has some maximum frequency cutoff that's lower than A side. Okay, so A side will be the side that has the frequencies that are higher. If you heat one side, cool another side, you'll get a temperature discontinuity at the interface, which we call the interface resistance, and the heat flow is just proportional to that delta T by the conductance. The phonon gas model picture is that you have propagating modes that will then impinge on that interface. Then they have some probability of being reflected or transmitted. Now, what's interesting about that is then you can go do the Landauer formalism, and what comes out of detailed balance is that you only need information from one side of the interface to actually describe the conductance. So we actually struggled with this for quite some time, and this was actually one of the reasons it took us so long to solve this problem, is because we were really trying to adhere to this criterion that you only need information about one side. But what I'll show you is some interesting stuff in terms of what selection you use for the coordinates for the modal analysis. So there are different choices for how you might want to break down an interface. One choice would be, I could say, let me just take material A, I'll treat it as an infinite crystal, I'll solve for the modes in that crystal, and I'll use that as the modal decomposition for which I'm going to project the atomic displacements and get the heat flow and all my results. So we'll call that A. I'll get 3 Na modes, and I can use the following expression to get the heat flow across the interface. Now, where the information about B enters in is in these forces. So these are the forces across the interface. So there is some information from B entering into the problem, but the velocities of the atoms are only on the A side. So I only need the modes of the A side to do this description. Second choice would be, what if I assume that I need information on the velocities of both sides? I could take one material A, get 3 Na solutions, material B separately, get 3 Nb solutions, and now I could just add them together, get 3 Na plus 3 Nb solutions. What I could do there is I could say the eigenvectors for a solution on the A side are all the eigenvectors I had, and on the B side, I will just treat them as though they are 0 and vice versa. Then I could use an expression that now integrates the velocities on both sides of the interface and incorporates both sets of information. One other choice I could do is I could say, what if I go ahead and form the entire system, make the interface and build it into the system, now do a lattice dynamics calculation on the entire coupled system. Now I will get 3 Na plus Nb modes all at once.
That's the periodic as well.
It could be, or I could actually make the ends free. I could make it really big and I could leave the ends free as well. Okay, so I could do both. If I do that, I could use the following similar expression to here to get the heat flow across the interface. All right? So I have these 3 choices for how I could project the modal information on it. We spent quite a bit of time trying to understand what's the right way. Are they all equivalent, or is one way right and another way wrong? And so we came up with a test. So the test we came up with was based on the wave packet approach, where what we did is we said, okay, let's take simple system, Lennard-Jones argon, make the other side argon, but I'll just change the mass by a factor 4. It's a simple, very simple interfacial system. It's fictitious, and people have studied this system before, so we know exactly what's going to happen. If I generate a wave packet, I throw it towards the interface. None of the other modes are excited. It's going to bounce off the interface. I'm going to see some reflection. Depending upon its frequency, I'll see some transmission, and all these things are very well established. It's a purely elastic scattering event. Now, what we said is if for the right set of coordinates, we're going to try and look at this wave packet test and do this modal decomposition of the heat flow and examine these 3 choices of coordinates and see which one satisfies all 4 of these conditions. So, first condition is the wave packet as it approaches, the total heat flow has to be 0. Why? Because none of the atoms at the interface have started moving yet. So if they're not moving, there's no heat flow across the interface. So even if there are modal contributions from different modes, they all have to cancel out and have to get 0 until the wave packet shows up. Once it shows up, the only contributions I should see that are transferring the energy across the interface should correspond to the range of frequencies associated with the original wave packet. I shouldn't get frequencies far outside of that because they are not excited in the simulation. So you could do a spectral analysis and you see all the atoms vibrate right in the original frequency range of the original wave packet. So any frequency content you see outside there is erroneous or fictitious or virtual excitation that's not real. Second criterion. If I integrate all those individual heat flows for all those individual modes, sum it all up, and integrate it in time, I should get the change in energy, how much energy was transmitted to the B side. Okay? It's basic energy conservation. Third, I shouldn't see any excitation at all outside the range of the original frequencies I excited. And if I integrate in time and look at how much energy is contributed across from each of those modes, I shouldn't see any net contributions outside either. So when we did this, I'll give you the answer up front, and then I'll show you a couple movies. This is using the modes on side A, modes on side A plus B, and AB together. So first thing you see is that all three are not the same answer. The second thing you see is that before the wave packet reaches the interface, all three of them are in between these pink lines. The pink lines are the original set of frequencies excited by the wave packet. But when it hits, you'll see that using the A modes, A plus B, you see significant broadening. You see peaks outside of that pink line, suggesting that somehow those frequencies are involved in the transport of the energy across the interface. And then once the wave packet finishes scattering, comes back, they all suck up into here. But this is the only one that stays inside the pink lines the entire time throughout the entire simulation. And so we think that this is now the right way to look at the system, is you have to treat the coupled interface together because that actually includes all the information about the cross interactions at the interface. And those are the correct modes that you want to use.
This is done in the harmonic limit or anharmonic?
This is anharmonic, but we're doing an elastic scattering event, sending a wave packet where no other modes are excited. So the wave packet event itself is like it's in the harmonic limit, but it's a fully anharmonic simulation. But none of the anharmonic characteristics are being utilized here.
Bob, besides the function of frequency, is a wave vector also in the nanostructure?
You can define wave vector for these two cases because these were based on the infinite crystals separately. But you can't define it here because not all these modes have wavelengths. So this is getting...
Are you using periodic? Are you using periodic clock?
Sure. So it is like a superlattice where it's periodic, but those wave vectors would correspond to the bulk motion of the entire cell. Those are longer vibrations than we're actually sampling here. That's like the bulk motion of the whole system.
If it's all harmonic, what do you think is producing those frequencies outside the initial range in those other
Excellent question.
formulations?
So the way I think about it is that using those basis sets, those modal basis sets, is incomplete. So it augments the fact that it can't actually describe what's happening at the interface by virtual excitation of other modes that are not actually being excited. It doesn't have the correct information to describe the event. And so the only one that does is the full coupled system, the actual system you're simulating. So I'll show you a movie. So this is using the modes of A. This is the wave packet itself. It's a longitudinal wave. This is the interface. This is just going to propagate forward and hit. You'll see some energy go through, some energy come back. This is the total heat flow. This will be 0 until it hits. Then you'll see it start oscillating as it's transmitting the energy across the interface. This is the integral of this curve. So you'll see this 0 start as soon as it starts to hit the interface. It'll oscillate, and then it'll finish at a positive number. That offset is delta E. That's the amount of energy that went through the interface. And then this bottom plot is what you saw on the previous curve, on the previous slide, which is the in time you're looking at the frequency spread, the contributions to the heat flow of all these different modes. So this is the range of modes we excited, is this range delta omega here. So if I use A, you'll see what happens. So I send the packet towards the interface. You just see these things oscillating. As the packet starts to reach the interface, the heat flow starts to pick up. I'm now transmitting energy across the interface. You see these things get out of phase, and you see this broadening. It's describing it as having contributions outside of this frequency range. And you can see when it's finished, you'll see this offset. This is the amount of energy that got transmitted through completely delta E. See, it's offset from where it started. So this broadening suggests that this approach, this way of viewing the problem, is problematic because It's not describing the frequency content appropriately. If I add A and B together, again, you can see I don't get the exact same answer. So this content looks a little different from the first time. And you'll see again, as the wave packet hits, you're going to see broadening. You're going to see peaks start to show up outside here as the energy is transmitted across the interface. Okay? So prior to getting to the interface, these modes were fine. They can describe the bulk behavior just fine. But at the interface, it's problematic. Now, if you take a look, this is normal incidence, yeah. Now, if I take the combined modes, the combined basis set, you'll see what happens. Everything stays right in this region the entire time. It's actually quite elegant. You'll see it looks like a sine wave, and then all of a sudden, as it's transmitting the energy, it goes in phase, pushes it across the interface, and then as it's finished, it goes back to wavy behavior and starts canceling out again. All right, so the reason this is significant is because when you use the modes for the combined system, not all the modes propagate, okay? And so we ended up identifying 4 different classifications of modes that showed up in the system. You see extended modes, ones that look just like a regular phonon with a sinusoidal amplitude variation, and it kind of shifts as it goes across to the other side. These are the low frequency modes. Then you see what we call partially extended modes. The majority of the modes are like this. They sit on one side, but they partially penetrate into the other side. So they decay a few layers of atoms into the other side. Then you have what we call isolated modes. These are modes that don't even reach the interface, so there's like almost no motion at the interface, so they transmit almost nothing. And
Periodic system?
say again?
So that's perfectly periodic thing.
Exactly.
What's that?
Exactly.
So what? How do you?
Exactly. So, and then we also have interfacial modes, which actually are peaked right at the interface. Even though this is like a periodic structure, you just have like a superlattice, but you'll get localization right at that discontinuity in mass. So again, the idea here is that the phonon gas model presupposes that all the modes kind of have this kind of character. They're either extended, they have clearly defined wavelengths, and you can define their velocities. But these interfacial modes can't be described by that formalism very well. I mean, it's difficult to rationalize what velocity would you use, what kind of transmission would you call it if it simply sits at the interface and doesn't approach and leave. So we then go and calculate the accumulation for these different modal basis sets, and you see you get, again, something very different. We tried equilibrium and non-equilibrium. We essentially get the same answer. Since now we're actually decomposing the heat flow itself, we can actually do non-equilibrium. We get the same answer. And what's interesting here is kind of for the first time you can see in a structure like this red line represents the maximum frequency on the heavy side. So all the contributions above this line represent inelastic scattering events. Somehow the energy has to change frequency to get into the bulk side of B if you got these modes above this frequency limit that are contributing. And so we can actually see, and we can see the temperature dependence of how the inelastic events or some kind of frequency conversion is happening. And again, you can see a significant difference between A and A plus B. The cool thing, this is what to me convinced me. I wasn't actually convinced until I saw this plot. If you take and approach zero Kelvin, so as you go to absolute zero, what you would expect is that somehow you should get rid of the anharmonic effects and you should go to the elastic limit, and therefore there should be no contributions above this frequency. And that's actually what we see with only the AB modal basis set. The others continue to show like these modes are significantly contributing. So as we go to very low temperatures, the anharmonic effects shut off. Okay. Now here kids.
Correct for the specificity.
Say again?
You correct for specificity.
So we didn't.
So
it's
right.
excellent. So excellent question. So here we didn't. So this is actually the raw MD result. Without any correction, you still see it flattens. Now what you'd see if you do quantum correct is you'll see that you got to reach 100% by even lower frequencies. So only these will really show the contribution. But we wanted to show specifically the anharmonic component goes away. So regardless of the specific heat cutoff, you see that this goes away. Now what's interesting is the contributions from these various modes. So the extended modes in this structure occupy about 10% of the density of states, but they do about 40% of the conduction of the conductance. Then you've got the partially extended modes. They're the majority, so most of the modes follow this kind of classification. They're 83%, and they do about half. The isolated modes, they're about 5%. They don't do much at all because, again, they don't even go towards the interface at all. The interfacial modes, there's very few of them, only a handful, but they do 3%. So on a per mode basis, the interfacial modes actually have the highest conductance on a per mode basis. So this got us very interested in the fact that you can't necessarily say, well, these interfacial modes are negligible just because there's a small number of them. They actually have a large contribution, and I'll show you another structure in a minute where these things actually have a very strong, much larger contribution than 3%. So it's not like you can say, I'll do the phonon gas model and do some correction just for these interfacial modes. So now looking at the cross-correlation plot. So this is now the correlation between different modes. So this is now frequency and frequency. This is, again, the symmetric plot. You saw it in 3D before. This is now plotted like a 2D plot. What amazed me when I first saw this is that there are actually features that arise. We didn't do any classifications of the modes. This is just plotting the nth solution without any predisposition on our own part. And you actually see a line show up right here. And this line corresponds to where you get the first mode that's localized. Below this frequency, these are all the extended modes. And you can see they interact very strongly with each other. Then, as soon as you see the first localized mode, the correlation has a distinct change and you see a valley. These modes in between here and here have a much lower interaction with everything else, and you actually see this region of low correlation. This frequency...
Localized modes, the interface modes, that's what they mean, localized?
No, localized meaning they're only on one side of the interface. So this is the onset of where you don't have modes that exist on both sides completely.
Component.
You do. So there is a diagonal component, but what's interesting is a good chunk of what's contributing here are the off-diagonal components. So it's the interactions between modes that are contributing to the conductance considerably.
On different sides of the interface for a second, right? So,
Second?
I mean, why don't you see a diagonal contribution even in that intermediate frequency range?
That's an interesting question. So what I think is happening is that these are the modes that are actually on the heavier side that only slightly penetrate into the A side. And it's interesting because they, for some reason, don't seem to interact with anything else. So even though you're right, there is an autocorrelation peak. If I plotted it in 3D, you'd see a ridge. It's just small. It's just much smaller.
What's the density of states? Maybe that's part of the answer.
Excellent question. So the density of states actually has a peak right in here, because this is the heavy side. So this is the heavy side's peak. So its longitudinal branch would end right here. So there's a peak in this range. There's lots of modes in there. They're just not correlated with each other. It's very odd.
This is just all different directions included?
This is everything, all together.
Why is it too? I guess I can't see it in this quite as clearly as in the earlier correlation plot, the 3D plot that you showed. But there was structure in it.
Yeah.
Why? I mean, again, if that corresponded to density of states, that would be easy to understand. Maybe it does. But why is that? Why are there sharp peaks?
Exactly. So I think, and this is just a hypothesis at this point, we have more study to do, more structures to calculate and look at, but I think that this vantage point of actually looking at the mode character itself, looking at their frequencies and how the extent to which they overlap with each other is a different vantage point that we need to take to understand why two modes would interact. So I think what you see there are overlapping regions where those modes might have significant overlap, where the polarizations or vectors are either similar or they have different directions in a particular region, where energy can really convert from one mode to the other. And so you'll see significant peaks where they're exchanging energy. They actually are exchanging the heat between them. It's also not clear if we do more ensemble averaging over multiple trajectories, if some of those peaks will weaken and you'll just see some very strong features show up at certain points. So that's some more averaging that we have to do to see if some of those features will smoothen out. On the right here, these are these interfacial modes. And so, one of the first questions we had is, okay, if you got interfacial modes, who do the interfacial modes interact with? And so this was kind of interesting that you can see a strong red peaks down here. So somehow they're interacting with the low frequency extended modes, and they're also interacting with the high frequency modes. So our initial thought is that they may actually serve the function of doing up and down conversion at the interface. They may actually help to convert the energy from the extended modes up, and from the high frequency modes that can't go into the low side, convert it down to an extended mode that can go. And so we're building some frameworks now, some new tests to try and test out some of these hypotheses as to what they're actually doing. But this, I think, is pointing us in a new direction to actually look for new things.
In your normal how a normal incident wave excite the interfacial mode? Do you have a picture?
That's one of the things I want to do next. So in the traditional wave packet approach, right, you have to silence all the other modes while you excite the wave packet, right? So you have no other contributions, no secondary coupling to anything. So what I want to do is just do a wave packet approach where we send a mode that we know has strong correlation at some temperature, and then excite a wave packet in the context of a finite temperature MD simulation, and see if we can watch and see what the interfacial mode actually does to the actual scattering event. See, the problem is if you do it in the wave packet approach, that mode is going to decay before it really reaches the interface, and you won't really know how much energy from the original wave packet got there. We can see it, we'll know when it got there, so we'll know when to look for the event, but we'll be looking at what does the interfacial mode actually do. So these are some of the tests that we're planning to do in the future to look into more into details. But here's another case that got us really interested. So take silicon and then a heavier version of silicon. So again, lattice matched, just change the mass. That's all I did. What's interesting here is the accumulation function has almost a step change. And this got me very, very excited because all the accumulation functions we'd seen were very smooth. They usually go from 0 to 1 in some very smooth transition. But we actually saw look like step behavior here right between 12 and 13 terahertz. So here's the interesting thing to your point. The density of states is not that big here. There's not actually that many modes here. So what's going on? It turns out there's like a handful of 4 or 5 interfacial modes that are actually responsible for 30% of the conductance here. So these modes somehow do a tremendous amount of conductance across the interface. Very interesting. So we then go and look at how big their conductance contribution is. Now you can say, well, what's the maximum conductance I can ever get from the phonon gas model limit? So the best I could ever do is I say a mode has the specific heat associated with its frequency. I give it the velocity, the biggest velocity I can find in the system. I'll give it the velocity of the speed of sound on the lighter side. Then I'll give it 100% transmission. So if I do that, I can now plot an accumulation function for that fictitious system using the same sets of modes. And what you get is this. And so right in here, you can see the slope. And so this slope, these modes actually have higher contributions than you could ever predict with the phonon gas model. So this, again, suggests that how you want to view these modes is fundamentally different than just some effective mean free path or some effective transmission coefficient. They literally behave very differently. And I think we need to widen the scope of how it is that we treat modes in these kinds of systems. And again, this is in the limit of contact between two crystalline materials. So I'm not introducing any structural disorder here. All right, last thing I want to talk about. I got about 7 minutes. I'm going to move really, really quickly through this. Last case we looked at was actually divergent thermal conductivity in polymers. This is related to what I did for my PhD work. We found another polymer that has a similar kind of behavior. It's polythiophene. And one of the key questions that I always had is, I was never really totally convinced that the divergence itself was not purely a function of the fact that we had periodic boundary conditions. So it seemed like the modes could travel, they could go through the simulation, they could stay correlated, and they could stay correlated indefinitely, but maybe somehow that was a function of the fact that you had periodic boundaries. Now, we always thought maybe you could extend the length of the boundaries, so the effects of the boundaries would get smaller and smaller, but I always wondered, is there another explanation? Can we really get to the heart of what's causing the correlation? So now that we had this GKMA method, one of the things we did is we identified some chains that actually had divergent conductivity. We found which modes are responsible. And so what I said is, why don't we do a simulation and let's get rid of the periodic boundary conditions. Let's take it away. So now you have a finite chain, and we plotted the thermal conductivity as you increase the chain length, where we've now fixed the endpoints. So there's definitely scattering right at the endpoints. What's absolutely interesting is right at 90 unit cells, these are the chains that we saw the divergent behavior in. You see a jump in thermal conductivity that jumps right off this trend. Was really, really interesting is if you go from 90 unit cells to 89 or 91, one more or one less unit cell, it falls right back down to this curve. So something absolutely anomalous is happening when you have exactly 90 unit cells in this system. So it's very, very interesting. So we see that at 90, and we also saw some of that behavior also at 150 unit cells. So this was kind of the first indication that something anomalous actually does happen in these systems with just this particular group of modes and how they tend to interact. We also see that the frequency content of going from 90 unit cells to 89 to 90 is significantly different. We see a significantly different peak. And what we found are the modes that are responsible correspond, this is coming from the heat flux, so this is like a factor of 2 difference, so the actual modes have a frequency of 0.05 terahertz, and it's the transverse modes at 0.05 terahertz that are actually responsible for the divergent phenomenons. We see a peak there in the heat flux. It's very interesting. So I have just a couple minutes left. I'm going to move through this really quickly. We actually tried a totally different method of trying to understand the origin of this phenomena. So when you plot the data, very often it just looks like a bunch of white noise. It just looks like a bunch of frequencies. You can't really see anything. And so even though we would try to zoom in and see, oh, can you see some scattering event, we never could really identify anything interesting. And I actually have a music background. And so I was always interested in what does this stuff actually sound like? What happens if you actually convert these signals to audio signals and listen to it? Will we actually hear patterns that you can't actually see with your eyes? The result was quite interesting. I don't have time to play it now, but if you're interested, I can play you some of the results for the polymer. We actually used sonification to actually identify what was going on in the polymer chain, and we actually found what is happening between the modes, and there's a certain recurrent behavior that you can hear in the mode heat flux for each mode. I'll play you another example now, just an example of material that everybody I know knows, silicon. So I'll play you what the sound of the velocity of an atom in silicon sounds like at room temperature, just so you can hear. The first thing, I didn't know if it was going to sound like white noise. I thought it was just going to sound like craziness. But it actually sounds like a very distinct sound. It's quite interesting. Let's see if I can get this to play. So if you listen to the low frequency content, you can actually hear a low frequency phonon get excited and then die down. You'll hear it pulse, woo, 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 and then die down. So we're starting to use this approach to actually try and uncover some of the underlying phenomena that's happening between phonons and their interactions. By actually listening to the data, we can actually identify some interesting patterns and some interesting phenomena. So with that, I'll just give my concluding remarks that basically the phonon gas model, is nothing wrong with it, works perfectly for crystals. We're just concerned that that may be the only case where it's rigorously correct. And that it seems to be somewhat inconsistent with the kinds of modes that you see in amorphous materials, alloys, interfaces, and the interface modes can actually be very significant. So again, I showed you a case where the interface modes, just a handful of them, were responsible for 30% of the conductance, and then even in the individual polymer chain, the only way you could explain the divergence in the context of the phonon gas model is to say one of these modes must have an infinite relaxation time in order to have infinite thermal conductivity, but we've shown that the relaxation times are actually finite. These modes are in fact interacting with each other. They are scattering. They do decorrelate in terms of their autocorrelations, but you see interesting cross correlations between modes. Somehow the scattering events themselves are remaining correlated in time, and they pass energy back and forth between them, and somehow that allows them to carry more heat. So with that, I'll conclude. I'll be happy to take any questions you might have.
When you change this polymer from 90 to 88 and so forth, do you think that reflects something that would really happen in the material, or is it basically a peculiarity of the simulation that brings out some particular, I don't know what, resonance or coupling or something, that happens to peak in a funny way?
I'm not totally sure whether I'm convinced it's definitely something that purely shows up in the simulation. Whether or not it might actually show up in reality is difficult to tell, but I do think there may be an interesting way to actually test it. So what's interesting is that the modes that are responsible for that large jump in thermal conductivity somehow are able to Again, you got to move outside the phonon gas model. So even though the chain is not very long, you can't think of it as though there's a mean free path and the only contribution I can get is the length, the time it takes for it to traverse the length of the chain. Now the thermal conductivity contribution is just a totally different animal altogether. It's just about how much it's correlated. So since these modes can stay correlated, granted when the chain is elongated, it may be possible that they exhibit significantly more correlation even when they're coiled.
Even when they're what?
When they're coiled up, like in an amorphous phase. So one thing I was thinking is if someone could actually take a polymer like this and make an amorphous polymer with a very, very narrow range of chain lengths, if you measure the thermal conductivity as you traverse chain lengths, you might actually see a bump where even though the chains are all coiled together, if this phenomenon is real, you might see a little bit of a deviation right around that point. Yes.
So your previous picture on your polyethylene was this two modes
Passing back and forth.
Cross correlation.
Yeah.
And going to so that's similar to Fermi's picture before, right? Fermi is going to other modes. It doesn't die down.
Exactly.
This is a different picture.
This is the same picture. This is just a little bit more detailed. So here we found it's like 4 modes and they're all correlated together. So it's the lowest 4 transverse modes in this particular system. Polyethylene was even more interesting because it wasn't actually the lowest frequency modes, it's actually in the middle of the dispersion that were responsible. But in this case, it's these lowest 4 modes. What's interesting is it's the lowest mode that seems to dominate and he shares it with something else and somehow it comes back.
So you have not figured out where the energy goes to other modes and come back?
No, but I'm working on trying to figure out a way to track that somehow. I think one of the easiest way to track it might be with the sound, where you can actually hear a fluctuation here, then hear a corresponding fluctuation somewhere else. Yes?
Could you go back to the point where you talked about the definition for the A and B? You mentioned something about, for the Landauer case, that there is information only needed on one side. Could you elaborate more on that? Because when you do F dot D for your heat flux, the information, like you said, is in the dynamics, so it's just a matter of choice. And maybe the second question was, since you're doing your Kubo on it, time-dependent heat flux, whether you take F dot D on one side or the other has different values associated with it because you're not in a steady state. So how do you choose between which one you take?
Okay, let me do the first question first. So what was interesting that came out of this when I was talking about Landauer and our struggle with that was actually because when we were writing down the math, we were trying to enforce Landauer to be true. And what we had to do was relax that constraint. It turns out it's still true, even here. So actually Newton's third law, that the forces are equal and opposite, is actually a microscopic version of detailed balance. So these 3 expressions for the heat flow across the interface are equivalent. They're actually identical. And so you can use information from both sides or you can use it from one side. It's equivalent. So that still actually holds. Okay, so that part's still true. But what it ended up being was an impediment to us finding the solution because we were trying to enforce that it was true, but a lot of the expressions we had didn't seem to make any sense of that because we were stuck on these kinds of expressions where we had information from both sides and we were trying to rationalize how am I going to use modal information from one side? What am I going to do with the other velocities? And so that became an impediment. But ultimately, the final result is still consistent with that. Your second question. Remind me one more time of the second question.
In a steady state, if you look at like heat moving away from the left path versus like the power entering the right path, they're the same because they're a steady state. But in this case, the interactions themselves are fluctuating energy, right? So whether you choose to make the energy flow from left to right be energy leaving the left interface atoms versus energy entering the right interface have slightly different values. How do you choose for consistency?
So they should be equal and opposite. I think if I understand you correctly, you're talking about whether or not you define the heat flow from A to B as positive or B to A as positive. Is that what you mean, or?
Like the energy leaving A versus the energy entering B are different because the interaction potential energy itself is changing.
So those two are the same because we're doing this in microcanonical. So the total energy is constant. So the only way energy can leave A is if it enters B. There's no other place for it to go. Yes.
I know very little about this. That's one reason I came to hear your talk. But what I'm interested in is what measurement experimental validation of the model concepts beyond these gross aggregate properties like conductivity is there. I treat it very generally. I'm just interested in how strong is this construct in some way?
Excellent question. I think when I saw this behavior, when I saw a very, very strong contribution from a very small subset of modes, that was the first time I thought that there might actually be a way to experimentally probe and see a significant change in conductance if you can, for example, silence these modes or somehow stimulate them or turn them on or off. That's one thought. The other thing that happens is that this green Kubo formalism has another dimension to it, which is that the conductance or the thermal conductivity itself is actually related. It's related to the frequency at which you perturb the system. So what we always take is the zero frequency limit of some steady state heat flow. But in reality, if you could actually perturb the system at very high frequencies where you, let's say, heat and cool and go back and forth, these accumulation plots change dramatically. So as you actually start to probe it very fast on the same time scales as the relaxation and the interactions between the modes, you'll actually see very distinct changes. And I think the only way you would be able to get that correct is if you had the modal description correct. So, for example, if you could somehow measure thermal conductivity or conductance as a function of perturbation frequency, I think you'll be able to really probe whether or not this description is correct. Yeah, another question?
How do you get isolated modes in the perfectly periodic lattice?
How do we get isolated modes in the context of a periodic lattice?
Yeah, I understand you get surface modes because there where you interrupt periodicity, right? But you get isolated modes somewhere else, right? That's what you're saying.
Let me show. You mean these isolated modes that are actually confined?
Yeah.
So there's not a lot of them, but they show up as solutions to the equations of motion. Actually, it.
Yeah, how is it possible? Because you know that for an infinite lattice you don't get them, right? So
Yes.
That means they somehow related to the existence of the interface, but you're saying they're far away from the interface.
Exactly.
Yeah.
So my hypothesis at the moment.
Find this isolated. It's just on one side.
Yeah, it's only on one side and it doesn't go to the other.
It doesn't match.
Yeah, so if you have a mode whose frequency doesn't match at all, there's no modes on the other side. Let me show you a case, actually.
Yeah, it should be extended on this one side. It will be extended, right? So how it could be local.
I forgot to acknowledge my students. All this work was basically done by two students, Wei Lu and Kirash Gordiz. This is my team at Georgia Tech. I also want to acknowledge funding from Intel as well. Let me see. Okay, so this is an example. This is indium gallium arsenide on indium phosphide. This is lattice matched. So this is an alloy and then indium phosphide. Indium phosphide is interesting because indium phosphide has a gap, a phonon band gap. So in between here, indium phosphide can't support any vibrations in the bulk of its material. And so when we do this whole modal analysis method, you see actually there's modes on the indium gallium arsenide side that are there. The density of states is there. What's very odd and very interesting about this system is we saw that the modes grouped themselves into the density of states. So you can see the extended modes occupied exactly just the region that overlaps for both materials. Right between the cutoff between you have now modes that are only on the indium gallium arsenide side, you actually had interfacial modes right at the overlapping region. Then at the next overlapping region, you had isolated modes and interfacial modes where you have now the modes that are only on the indium phosphide side. So this was kind of odd. None of the other systems seem to organize itself this way naturally. I don't know if one can define a general set of rules. We haven't tested enough things for those rules to emerge yet. I do think they may come out over time as we look at lots of different structures. But those isolated modes, yeah, they do get confined to one side and they don't go near the interface. It's very odd. But this is direct, what to me proves, right, so you can test the lattice dynamics calculation by just stimulating that one mode and just let's see if it immediately couples. That means that the mode you defined is incorrect for that system. But we can stimulate all these modes and they'll just sit there for an entire nanosecond, just oscillate by themselves. Do you have a question?
I'm curious, so you start with, say, a crystal, and you work your way towards a binary alloy by gradually increasing the constituents of one of the materials. Do you see an evolution from, say, propagating modes that go into the propagons, and then, say, the optic modes, the acoustic modes going into propagons, and optic modes going into these locons, like is there the same kind of frequency range, roughly? Or?
That's the next thing we're testing. So I have a student that's working on it now. I don't know the answer, but that's exactly what I'm expecting, is that right in that probably 0 to 10% composition range where you see the thermal conductivity drop real fast, I bet what's happening is that is actually a transition between all propagating behavior, and now the majority of the modes at probably 10% or above become diffusion-like. So we're working on it now. We'll probably have it soon, a couple months. Yeah.
You know, people have made some measurements of what since it's sort of microscopic, they wouldn't refer to as thermal conductivity, but just vibrational energy transfer from one side of the molecule to another, or even somewhat longer molecules, where there's something you could think of as a chain. How much of that applies to some of these issues where you're not looking then at mostly propagating modes? It's just vibrational coupling.
That is exactly the reason we developed this formalism. So we can do an individual molecule with just its individual modes now.
Well, even back, I remember a long time ago, Orbach looked at heat transfer in glass, right? Mm-hmm. Looking at the same sort of vibrational energy transfer. I think that was with an eye toward trying to understand thermal conductivity, but still very much with the notion of looking at these sort of quasi-localized modes. In the way that physical chemists like me would talk about vibrational energy transfer. The underpinnings are pretty similar, right?
Mm-hmm. Yeah, absolutely. Yeah, I think the key step I think that's going to be interesting in going down this path is when you see these other modes that are not propagating, what's going to be our physical representation in our mind about how they move heat from A to B? That's the part that I'm still struggling with and still trying to define and invent new tests to actually try and see if we can figure out what they're doing.
Okay, I think we're going to wrap up here.
Okay.
Thank Ase for the great talk.
Thank you.